So earlier, when we had more than one event, we could look at the conditional probability, because the conditional probability of B given A was what's the probability the event B happens, given that we know that the probability that the event A happens. What's the probability that B happens, given that we know that A happens? So we can ask the same thing with random variables. We could say, what's the probability that Y takes a given value, given that we know what value X has taken? And so once we know one random variable, what its outcome becomes, then that might tell us something else about a new random variable. So you'll remember that we had the definition for events, the probability of B given A being the probability of A and B divided by the probability of B. And so similarly, for random variables, RV's random variables, we could have the same thing, which is the probability that Y takes some value little y, given that it takes some value little x, would be the probability that they both happen, divided by the probability that the thing we're conditioning on. Now, those things on the right-hand side of the equal sign, we can write those in terms of joint and marginal distributions again. Right? On the top, we have the joint distribution, pxy over pxy, and on the bottom, we've got the marginal px of x. So it seems natural that the thing on the left we should call the conditional distribution, or the conditional probability mass function. It seems that we ought to call that py given x, y given x. So we can call that the conditional probability mass function, and that there is the definition of the conditional probability mass function. So, for example, if we know that x equals 1, say, then we have the conditional probability of some particular value, let's call it just little y, given that x equals 1, equals the probability that x equals 1 and y equals little y over the probability that x equals 1. So it's useful to think of this in terms of the joint distribution table we had back before this table here. Because this is telling us that to get the conditional probability given x equals 1, we take the probability of y and x equals 1, which is this row of the table here, and then we divide through by the probability x equals 1. So in other words, that means we have to renormalize that row of the table such that it adds up to 1. So that would mean dividing everything by a half, the number in the circle on the right, or if you prefer, multiplying everything by 2, because that would make that 0, quarter, quarter, 0. That would make it 0, a half, half, 0, and that would add up to 1. So the conditional probability there is the probability y given x of y given that x equals 1. And those are those numbers in red, 0, half, half, 0. We're taking the x equals 1 row and we're renormalizing it so that it adds up to 1. Similarly, if we wanted, say, the probability distribution of x given y equals 2, so the probability, this time x given y, the other way around, of some x given that y is 2, that would say we had to look at the y equals 2 row, and we had to normalize by dividing by 3/8. So that would become 0. A quarter is twice as big as an 8, so that would have to be 2/3, 1/3. So again, we get the conditional probability distribution given y equals 2 by taking the y equals 2 column of the table and renormalizing it so everything adds up to 0, which is equivalent to dividing through by that 3/8. And so if we go back to where we were, you can see that that's what that formula says, right? We're taking the x equals 1 row and dividing through by its total. And similarly, the other way around, what we did was x given y, x2 was probability x, y, x2 over the probability y of 2. And that meant to take the y equals 2 column and renormalize everything. The good thing here is that other things that we've learnt about conditional probabilities for events carry through to conditional probabilities about random variables. So perhaps the most important of these is Bayes' theorem. You remember Bayes' theorem for events. Bayes' theorem for events was that the probability of A given B is probability of B given A, probability of A, the probability of B. So similarly, we can do this for conditional probability mass functions. Right, so for random variables, we also have Bayes' theorem, which says that the conditional probability of x given y is related to the conditional probability the other way around of y given x. But then you have to remember to multiply by the probability of x, the probability of y. And so that's just really what you get from replacing A by the event big X equals little x, and B by the event big Y equals little y. That, it turns out, will be quite an important result near the end of this course, where we will use Bayes' theorem for random variables in our study of Bayesian statistics. Incidentally, we can check that this holds for the example we were doing earlier with the coins, where we were looking at x being equal to 1 and y being equal to 2. So with the coins example, the left-hand side of Bayes' theorem is p x y 1 2, and if we look back to where we were, p x y 1 2 is that 2/3 in blue in the middle there. So that's 2/3. And that's the left-hand side of Bayes' theorem, whilst the right-hand side of Bayes' theorem is this product pxx, so px1, py given x, 2 given 1, over py2. Probability x equals 1 was the probability of getting one head and one tail from the first two. Probability y equals 2, if you remember back, that's a probability of getting 2 from a binomial 3.5, which was 3/8. And the probability y given x of 2 given 1 is that red number 1/2 there in the middle. The probability y given x of 2 given 1 is that number 1/2 just there. So if we put all that together, 1/2 times 1/2 divided by 3/8, that comes out as 2/3, which is the same as the 2/3 on the left-hand side. So there we verified that Bayes' theorem for random variables works, and that's an important result for conditional distributions of random variables.